Let me start by thanking the organizers for inviting me to give a talk. I was more or less thrown into this as a substitute for another speaker. And when presented with the opportunity to come to CERM, I was so excited that I immediately accepted, and only afterwards realized that I don't really have results that fit with the main topic of this, nice conference. So this is my excuse, or rather explanation, for giving a talk which is slightly off topic, but hopefully I will be able to entertain you nonetheless. So I will be talking about bounded remainder sets for the discrete and continuous irrational rotation. This is partly joint work with Nir Lev from Bar-Ilan University, and partly joint with Gerhard Lacher, who is also in Linz. So that's more recent, this continuous irrational rotation. But I will start with the discrete irrational rotation. So let me just begin by introducing some notation. So I will start on the d-dimensional torus, and alpha here will be a d-dimensional vector where the entries alpha1 to alpha d and 1 are all linearly independent over the rationals. So I will just refer to alpha as an irrational vector. And the classical equidistribution the classical equidistribution theory says that in this case, this sequence n alpha is going to be equidistributed on the torus. Meaning that if I, let's see here, count the number of points among the first n multiples of alpha that hit the set S, so this chi here is my indicator function, and I divide that number by n, then this is going to tend to the measure of S, the big measure of S, as n tends to infinity. And this will be the case for any starting point for my irrational rotation, that's this x right here. And any set S whose boundary has measure, or any measurable set whose boundary has measure 0. So that's what I'll be assuming about S for now. Now you can measure this equidistribution quantitatively by looking at the discrepancy function, which I will denote in this way. So this is now the difference between the number of points that are actually hitting my set S and the number of points which I expect to hit my set S, which is n times the measure of S among the first n multiples. And this classical result is saying that this difference is going to be lit O of n as n tends to infinity. Now, naturally, one could ask, are there any sets S or any special cases of alpha where I could do even better? And there are many points of view from which one could try to answer that question. And perhaps the more common approach is to look at the supremum or some other norm of this discrepancy over some family of sets S. Now, I will not be doing that. I will be fixing some alpha, rational alpha, and I will be asking, are there any particular sets S for which this difference is particularly small? And it turns out that for very, very special sets S, this difference can in fact be bounded by a constant. So these are the sets that we are going to be interested in. These are the bounded remainder sets. So let's start by reviewing what is known in one dimension in the very simplest case where this S is an interval. There is a result which is now nearly 100 years old by Hecke and Ostrowski that says that if the length of this interval belongs to Z alpha mod 1, then necessarily this discrepancy is going to be bounded as n tends to infinity. And the the converse statement was conjectured by Edison Seuss and proven by Kesten, this was 40 years later, that indeed the discrepancy is bounded only if the length is of that specific form. All right. All right. So if we look at the same phenomenon for more complicated sets and in higher dimensions, we need a proper definition to work with. So this is going to be my definition of a bounded remainder set. I'm going to say that S is a bounded remainder set, and I'll just write BRS from now on. If you can find a constant C, which might depend on S and alpha, but which will certainly not depend on X or N, such that this discrepancy in absolute value is bounded by the constant c. And this holds for all n and almost every x. Now this almost every x is fairly natural. As far as I can understand, it's just a matter of not changing this property by changing your set S on a set of measure 0. And if your S has boundary measure 0, this is the same as asking that this holds for a single value of x. Now so far we have been talking about this on the torus, but you could also extend this definition fairly naturally to sets in Rd. So let me just make a small drawing. In R2, for instance, if my set is something like this, then I simply take the canonical projection onto the unit square. So that's going to look like this, sort of. And I take this chi of s rather than the, let's see, where's my, there it is. This chi of s to be the multiplicity function for my set rather than the indicator function. So it takes the value 2 here, the value 1 here, the value 0 here. And if we do that, then we can easily extend this definition by precisely this statement to any set S in Rd. And if we do that, then what we had on the previous slide is that any interval I is a boundary remainder set if and only if its length belongs to this set. All right, perfect. Now, in light of this, I will ask the question, well, what about higher dimensions? Do we have a higher dimensional analog for this result? And when we started to look at this question a few years ago, this was apparently still a wide open question, which was a bit of a bummer because we really wanted to know what these sets look like for reasons I won't get into today. And in lack of a better alternative, we started trying to basically guess what they might look like. And we were very pleased, I would say, when we were able to show the following, namely that in higher dimensions, any parallelotope spanned by d vectors v1 to vd, all in z alpha plus zd, is necessarily a boundary remainder set with respect to alpha. Right, so if we look at this in just one dimension, then this reduces to the sufficient condition by Hecke and Ostrowski. So at least it's some kind of partial analog in higher dimensions. And in our original paper, we showed this by combining mainly Fourier analysis with some geometrical considerations. It's a nice proof, but it's fairly long. And a few years later, it became clear that you can also show this by a very, very different approach, which to me at least is somehow easier, and it fits better into the time frame of a 40-minute talk. So I will shortly get back to the proof of this result. But before we do that, let's also see a couple of necessary conditions. So it was shown by Fürstenberg, Keynes, and Shapiro, and this was in '73, that if you have a boundary remainder set, then its measure must necessarily be of this specific form, where the n0, n1, up to nd are all integers. So there are only countably many possible values for the measure, and these can all be realized. This was shown by Halas in '76, I think. Now, what we showed in our paper is that they can all be realized by one of these boundary remainder parallelotopes. So if you give me a measure, any measure, then I can, in 2 dimensions, for instance, find one of these parallelograms. Such that my parallelogram has that specific measure. And I will shortly get back to why this is important. Right. Now, another thing that we were able to establish was a new necessary, quite different necessary condition. And in order to fully explain that, I will have to introduce this notion of equidecomposability. So I'm going to say that two sets, S and S prime, are equidecomposable or scissors congruent if I can take one of the two sets, say S, partition it into finitely many measurable subsets, and shift these off, sorry, not necessarily shift, but rearrange them using rigid motions to get the other set, S prime. And if I can do that, I'm going to use this tilde notation to indicate that that is the case. Now, if these two sets, S and S prime, have some restrictions, say they are parallelotopes or they are Jordan measurable, then we're going to assume that the sets in the partition have that same restriction. And finally, I will not be interested in sort of general equidecomposability, but rather restricted equidecomposability, where I'm not allowing all rigid motions. So for instance, in my drawing here, I'm using only shifts. There are no rotations involved. Now, the specific type of restricted equidecomposability that I will be interested in is the following. I'm going to use this tilde notation with a small alpha to indicate that the sets S and S prime are equidecomposable using only translations in this set. So only translations by vectors in ℤ+ℤd. And it's fairly easy to show that if it's the case that S and S prime are equidecomposable in this restricted alpha sense, and one of them is a bounded remainder set, then so is the other. However, what we were able to show, which at least to me is far more surprising, is that in the case that S and S prime are Jordan measurable, so their boundaries in measure 0, you actually have the converse statement, that they have to be equidecomposable in this sense. So this was our second main result, that if S and S prime are both Jordan measurable boundary remainder sets, then you can construct one from the other by this partitioning and shifting by elements in ℤ+ℤd. So together with our first main results, this gives a full characterization of the Jordan measurable boundary remainder sets. Basically, if you give me a measure, then I can construct my, in 2 dimensions, parallelogram. I can partition it into finitely many subsets, which I can then shift off by these vectors in ℤ+ℤ2. But then this is also all the freedom that I have. There are no other sets that I can possibly come up with that have this special property. All right. Okay, so let me return to this sufficient condition and to the proof of it. As I said, originally we were showing this using Fourier analysis and geometric considerations, basically. But you can also show this by using so-called cut and project sets. And since I don't know how familiar you are with this construction, let me briefly explain what these sets are. Suppose you are looking at a lattice in the direct product of Rm and Rn, and you assume about this lattice gamma that it's in general position, by which I mean that if I now look at the projections onto either Rm or Rn, then restricted to the lattice, these will be injective and have dense images in Rm and Rn. And then, rather than looking at all points of my lattice, I only consider those whose projection onto Rm would necessarily fall into the set W. So this is W for window. So I'm only considering these sets. You can sort of see the gray strip there. So I'm focusing my attention on these points, and finally I can construct my cut and project set by projecting these points onto Rn. So I get a point set in Rn. All right. So this is now what I will refer to as the Meyer cut and project set. So I've taken P1 to be the projection onto Rn and P2 to be the projection onto Rm. And this construction was, as far as I know at least, introduced by Meyer in the 1970s and gained considerable attention about 10 years later with the discovery of quasi-crystalline materials. So this is a good mathematical model for quasi-crystals because it has a bunch of very nice properties. First of all, it is uniformly discrete and relatively dense. It is not periodic, but it has some it's sort of very ordered in a sense that I won't really get into. What will be most important to us is that it has a well-defined density, which under some mild regularity conditions on, here we go, on this set W, is, as I said, well-defined and only depends on the measure of this set W and on the density of our lattice gamma. All right. Now, we will not be interested in any, just any cut and project set, but rather a particular one, which is the following. We take M to be D and N to be 1. So we are now in RD times R1. And I'm going to call my window S, just to match with what I was talking about previously. Moreover, I'm not considering any lattice gamma, so I'm considering a very particular one, which is this one. And this looks a bit messy, but these are the important details. Alpha and beta are now d-dimensional real column vectors. And under specific conditions on these two vectors, this will be a lattice in general position. Now, the important details are, first of all, this beta, I won't be talking too much about, but remember that it's bounded, whereas this alpha is necessarily an irrational vector. And my cut and project set is now going to be of this form. So over here we see we have this n alpha plus m in S, so you can sort of start smelling the connection to bounded remainder sets. And I also want to point out that the projection onto RD here is precisely Z alpha plus ED, which is clear from this last coordinate. All right. And now, people studying these sets, among other questions, have asked, when will such a cut and project set necessarily be at bounded distance from a lattice? So precisely what we're asking is, when is the set X, which is now, again, a general bounded remainder set, a general cut and project set, at bounded distance from some lattice in Rn, meaning that we can find a bijective map from X to the lattice, such that this supremum is always bounded. And this norm here is now just the regular Euclidean norm in Rn. And it was shown by Dunant and Ogoé, and this was in 1990, in what was basically a physics journal, that if your window is a fundamental domain of a lattice in P2 of gamma, then the resulting cut and project set is going to be at bounded distance from a lattice. So if we now take this result and translate it to what it says for our specific case with this cut and project set, it's saying that if S is a fundamental domain of a lattice in Z alpha plus ZD, which for instance covers any parallelotope spanned by D linearly independent vectors in Z alpha plus ZD, then this resulting set is going to be at bounded distance from a lattice. Now, seeing as X is in one dimension, this means it's at bounded distance from an arithmetical progression. And finally, because this cut and project set has a well-defined density, we know precisely which arithmetical progression it's going to be at bounded distance from, which is this one. Now, I didn't state specifically that the density of the quasi-crystal of this set X is going to equal the measure of S, but hopefully you will trust me that it will. All right. So now we are getting close. This is telling us that if we can now just show that if our set is at bounded distance from this set, then it is a bounded remainder set with respect to alpha, then basically we would be finished. So finally, this is what we're going to see. And this is fairly easy to show. So if we now return to our set X, we see that we can partition it into blocks Xn, where Xn looks like this. And if we are now looking at some large interval 0 to k, and we count the number of points hitting that interval, then necessarily, rather than counting the points as we find them, 1, 2, 3, and so on, we can count all the points in the block xn at n. So necessarily, this is going to cause a constant error, but it will be a bounded error. So basically, we take capital N to be the number of points in the set X to this large interval. Then this is the number of points in these blocks plus some constant error, bounded error. And this in turn is precisely equal to chi-s of k alpha, because we see that the number of points in Xn is equal to the number of integer vectors m such that n alpha plus m belongs to S. So necessarily, this n is equal to this sum plus some constant error. On the other hand, you could, of course, just count the elements of the arithmetical progression, seeing as it's a bounded distance from that progression. So this amounts to counting the points in this set, in that interval, which is precisely k times the measure of S. So these two quantities differ by at most a bounded constant, which is precisely saying that your set S is a bounded remainder set. All right, perfect, perfect, perfect. So, right. Of course, some of you at this point might be sitting here thinking, well, now, surely I used this result by Dunot and Ogoue, and that might be very, very deep and hiding all the difficulties. I am going to claim that it really is not all that deep. It's a geometrical argument. They simply construct this bijection between the two sets. And of course, you have to be careful, but it's not difficult, I would say. So in my personal opinion, this proof is easier than the one that we originally found. Moreover, this is stated in a slightly more general form in a paper by Haynes, Kelly, and Vusalo. Now, I don't remember the precise title of the paper, but it definitely contains the word cut and project sets, and it's posted on the archive in 2016, so it should be easy to find. Finally, some open problems in the discrete setting. First of all, at least in my opinion, this sufficient condition with the bounded remainder parallelotopes seems to be fairly well understood now. You have some different proofs, and you have this connection to the bounded remainder sets, to the cut and project sets, which, at least in my opinion, is quite nice. And the result has sort of been available for quite some time. It's just been a matter of connecting the dots. However, this equidecomposability result seems to me far more mysterious. And when I was planning my talk, I was thinking, okay, we have this one proof. Could we possibly find a proof that is also somehow connected to cut and project sets? But now I'm starting to think that maybe the more interesting problem is, can you take this result about the bounded remainder sets and use it to find a necessary condition for these cut and project sets to be at bounded distance from a lattice? Because I think this is also an open question, as far as I know. Finally, a question which is of some personal interest to me, which is the following. And I know that I mentioned this to Christoph several years ago, so hopefully maybe he has an answer for me now. Suppose you're looking at the sequence of discrepancies starting at 0. And you ask the question, are there any sets S for which this sequence is unbounded but belongs to BMO? So for which we know that this inequality holds for all n smaller than m. And as far as I know, the only thing that is already known is that in the one-dimensional case of simply looking at intervals, the answer is negative. So for an interval, if you have this sequence belonging to BMO, then this already forces the measure of the interval to belong to z alpha plus z. And accordingly, the discrepancy is actually going to be bounded. But if anyone has any ideas on what would be an example of such a set in higher dimensions, or an idea of how to show that this is never the case, then I would be very interested. All right. Now, finally, you could ask, or you could sort of look at the analogous situation in the continuous case. So that is what I will continue talking about. So in the continuous case, and this is more or less wide open, we have, so together with ℤ+ℤd, I have looked at this only in 2 dimensions. And in two dimensions, we have the following situation. Suppose that alpha is some positive irrational, and x is some starting point in the unit square. Then I can look at the function capital X going from all positive reals to the unit square, given here. And I've drawn x here with starting point 0 and for some time interval starting at 0. And then again, we can look at the discrepancy between the sort of the time that x is spending inside of s, which is this quantity, and the time we are expecting it to spend inside of s, which is t times the measure of s, and ask how big is this discrepancy, and are there any special sets for which it would be particularly small. Now, I want to start off by mentioning a result by Joseph Beck, which I find quite interesting, which says the following. Suppose in the unit square you have any set S, which is an arbitrary Lebesgue measurable set with positive measure. Then for every epsilon and almost all alpha, we necessarily have that this difference is little o of log to the power 3 plus epsilon of t. So as pointed out by Beck, this log factor is surprisingly small compared to this linear term t. And this holds for arbitrary Lebesgue measurable sets S. So naturally one could ask, what if I now impose some restrictions on my set S? Can I then force the error to be even smaller, or the difference to be even smaller? And we have at least been able to find a partial answer to this question. Together with Lacher, we were able to show the following. First of all, if S is a polygon in the unit square, then this discrepancy is going to be bounded in absolute value as t tends to infinity for almost every alpha and every starting point in the unit square. And moreover, if S is a convex set whose boundary is twice continuously differentiable and has a positive curvature at every point, then you have the same property that this discrepancy is bounded in absolute value as t tends to infinity for almost every positive alpha and every starting point x. So the situation is really very, very different from the discrete setting. And I will try to give a very short outline of the proof of this first result in the simplest case where the set S is just a triangle. So this is, of course, just a one-dimensional problem, really. Once we know where our function capital X is hitting this side of the unit square, we know precisely how much time it's going to spend in S on that turn around in the x direction. So we associate to the set S this function tau of S, which is defined here by this integral. And I tried to draw a geometric interpretation of that tau down here. And we see that if we just plot the function tau, then it's going to look more or less like this. So this is what I'm going to refer to as a hat function. And showing that this discrepancy with respect to the continuous t is bounded is necessarily equivalent to showing that this is bounded. So this is the same as saying that this tau of S is a bounded remainder function for the discrete irrational rotation in one dimension by alpha. And this is what we then show basically in the following very, very shortly sketched way. Given any alpha, we write its Ostrowski expansion to base alpha, which it has a unique expansion of this form. where the qi's are now the best approximation denominators of alpha. And then we impose a condition on alpha. So this is now the continued fraction expansion of alpha, and we impose this condition that this quantity is less than some constant. So this will be the case for almost every alpha, where again the qi's are now the best approximation denominators. And given that you have that condition on alpha, you can easily show these two inequalities. So first of all, that you can approximate this sum by simply looking at these evenly spaced points that are 1 over QL apart. And moreover, that this sum over the evenly spaced points is necessarily at bounded distance from n times this integral. And combining them, you finally reach the point where you can show that this tau of s is indeed a bounded remainder function. So I think, let me see. Right. I wanted to mention two more things, or rather two open problems. First of all, as far as I can tell in our proofs, these conditions that we find, they are indeed sufficient, but there's nothing indicating that they are necessarily necessary. So it's my belief, at least, that there are also other sets that will be of bounded remainder with respect to almost every alpha. And for instance, I'm tempted to suggest that every convex set S might possibly be a bounded remainder set with respect to almost every continuous irrational rotation. And of course, in higher dimensions, this is still more or less widely open. We never looked at the higher dimensional case, basically because it got a lot more involved. But I'm sure it should be able to establish some conditions that would allow one to bound the discrepancy for sets also in the higher dimensional unit, cube, or interval. And with that, I think I will finish early. Thank you all for your attention.